Okay, real gases, liquids, and solids. So let's review the ideal gas law. If you remembered, the behavior of gases can be described by this equation right here, PV equals nRT. What's P? Pressure of the gas. V is the volume of the gas. T is temperature of the gas in Kelvin. N is number of moles of gas particles, and R is a constant. Okay, and that's the same constant for all gases. Well, that equation actually has limited validity. Okay, and the validity of that equation is this: it's true for all gases at very low pressure. So when pressure approaches zero, that equation holds for all gases. Okay, and so what will be the value of PV over nRT when P approaches zero? Well, if PV is equal to nRT, if you divide PV by nRT, that's going to be equal to 1, right? So we say a gas is behaving ideally if it obeys PV equals nRT, or you can say if PV over nRT is equal to 1. Now, typically, you'll be in error. If you use this equation, you'll be in error by about 1% at ordinary conditions. Okay, at STP, for example, room temp or close to room temperature, 1 atmosphere pressure. So it's a pretty good equation to use under ordinary conditions. But, like I said, that equation is not really true under all conditions. It tends to fail when you get to higher pressures. Okay? So, and it also tends to fail when you are at very, very low temperatures. Because what happens eventually at very low temperatures? What's the prediction of the ideal gas law versus temperature? Volume decreases and eventually it goes to zero, right? So it remains a gas, no matter how cold you make your gas, okay, it will stay if it's behaving ideal, it's going to remain a gas and its volume will just disappear when you get to absolute zero. Well, what happens to a gas when you actually cool it? It turns into a liquid. Okay, so it ultimately at low temperature starts to fail. Now, so how can we tell if a gas is behaving ideally? Like I said earlier, what you do is you measure P, V, T, and N, and how can you tell if it's behaving ideally? You calculate Z. Z is called the compression factor or compressibility factor. So it's equal to PV divided by nRT. And so if the gas is behaving ideally, PV is equal to nRT, so PV divided by nRT will be equal to 1. So the compression factor of a gas is equal to 1 if it's behaving ideally. Okay? Otherwise, if you see deviations from 1, okay, then you're going to get a value of Z that's significantly less than 1 or greater than 1. So that's how you can tell. All right, so why is Z called the compressibility factor or the compression factor? Well, let's see. Z is equal to PV over nRT. So let's compare an actual gas, a real gas, with the gas if it were behaving ideally at the same pressure, temperature, and number of moles. Okay, let's compare the volumes. So Z, okay, for a real gas would be pressure times volume over nRT, and this volume right here is the real volume. Okay, that's just PV over nRT. Now, if it were ideal, then Z would be equal to 1. So pressure times the ideal volume over nRT would be equal to 1. Okay? So what can you show from here? Z is equal to what? You can show that Z, let's divide Z by Z ideal here. Okay? What do you get? So, let me write this down here. Z equals PV over nRT, okay, over Z ideal, which is 1. PV ideal over nRT. So at the same pressure and temperature, okay, same number of moles, R is a constant, Z over Z ideal is just V over V ideal. Okay, but Z is just Z ideal is just 1, so Z is really just the ratio of the volume of the gas for that temperature and pressure. You compare the volume of your gas that you measure, compare it to what you would calculate as the volume of the gas using the ideal gas law. Using PV equals nRT, calculate the volume of the gas. That will give you your Z. Here's another way of looking at it. The ideal volume, okay, since PV ideal equals nRT, the ideal volume is equal to nRT over P, right? So you can say then that Z, which is PV over nRT, you can write that as volume divided by nRT over P, right? All I did was I divide both numerator and denominator by pressure. But what is this down here? That's the volume you would calculate if the gas was behaving ideally. So in other words, this is the actual volume divided by the ideal volume. So why is Z called a compression factor? Because it tells you how the volume compares with the ideal volume. So if Z is less than 1, what does it mean? Then the real volume is less than what you would expect if it were behaving ideally. If Z is greater than 1, then the actual volume or the real volume is greater than or bigger than what you might expect if the gas were behaving ideally. Okay? So let's illustrate that. 1 mole of a gas sample at STP has a molar volume of 22.0 liters. What's the compression factor? What's my Z? It's equal to what? PV over nRT, right? Or it's equal to volume over volume ideal. What's the volume of the gas given here? 22 liters. What's the ideal volume of a gas? If a gas is behaving ideally at STP, what's the volume? Do you remember? Volume of an ideal gas at STP. 22.4 liters per mole, right? Okay. So if you don't remember, you can plug in V ideal here. V ideal is nRT over P. And this will come out to be 22.4 liters. We're dealing with 1 mole, so let me get rid of that. Okay. So it's just 22.4 liters. So liter cancels out. And what's my Z then? What number would that be? 22 divided by 22.4. So that's going to be 0.982. So your compression factor is, or compressibility factor is 0.982. Okay? So I calculate Z. So how do we explain deviation from ideal behavior? Well, first of all, let's understand what ideal behavior means. Okay? So remember we said the limit of Z as P approaches 0 at very low pressure, the value of Z is going to approach 1. That's ideal behavior, right? And this is true regardless of what your gas is. Why doesn't the nature of the gas matter at very low pressure? In other words, why is PV equals nRT applicable regardless of what the structure of your gas is? It doesn't seem to matter what kinds of atoms make up the molecules in your gas. The reason for that is at very low pressure, what do we know from the ideal gas law? At very low pressures, your molecules are very, very far apart, right? Very large intermolecular distances. In other words, they more or less move independently of each other. There's negligible interaction between the molecules on average. Okay, so it doesn't matter what their structure is. It doesn't matter how strongly they might attract each other because they're so far away. Okay, so attractions and repulsions are negligible because the molecules on average are very far away from each other. So that's the explanation for ideal gas behavior. Very low pressures, they're very far apart. It doesn't really matter what kind of molecules make up your gas. So that's why you have that one equation that works for all gases. But what happens at intermediate pressures. Once you get these molecules a little bit closer, then you start to see deviations from ideal behavior. Okay? It's like saying that if someone's very, very far away from you, okay, you have minimal interaction with that person. It doesn't matter if that person's gorgeous or ugly. Okay? But if it's a little closer, you might see some attraction there. And if the person gets too close for comfort, then you start to repel that person. All right. So experimentally, z can be less than 1. Why? Well, when the average distance between molecules are such that the attractive forces are no longer negligible, so if that person is close enough so you can now see how gorgeous that person is, then you start occupying a smaller volume. So when the pressure is high enough so that the average distance between the molecules is such that attractive forces start to become important, okay? Then if there's attractive forces, then that means the molecules will occupy a smaller volume than they would if they were just ignoring each other. So that would lead to z being less than 1. So your volume is going to be less than ideal. Okay? Now what happens, how can z be larger than 1? Well, typically z becomes larger than 1 when you are at very, very high pressure. So you're trying to squeeze all these molecules closer together. Okay? So once your distance at very high pressure, you're trying to squeeze your molecules into a very small volume, they now start to repel each other. Okay? They're now, okay, it's like saying you're not invading into my personal space. Okay, so we start to repel. And so when the distances are such that repulsive forces start to predominate, the volume of the gas, okay, the molecules are going to spread out so that the volume of the gas would be larger than what it would be if they were just to ignore each other. Okay, so that's what happens. That's how Z becomes larger than 1 at very high pressures. Okay. So here's a typical graph that you can use to show how the compression factor Z depends on pressure. This is for carbon dioxide and nitrogen at 350 Kelvin. Okay? Which one do you think is carbon dioxide and which one do you think is nitrogen? This is a plot of Z versus pressure. Okay, so increasing pressure here. Notice that as you go to very low pressure, what value does the Z value approach at low pressure? What's this value right here? Z approaches 1. Okay? And so as the pressure increases, it dips below 1. Okay? And this one dips a lot. Eventually, that's going to go back up. This one dips a little bit, and then it goes back up. So eventually, that Z exceeds 1 at very high pressure. So let me see if you can reason out which of these two. This is what do you call an isotherm, by the way. This is it's constant temperature, okay? All of these data points are done at constant temperature, 350 Kelvin. So it's just Z versus pressure. So each one of these lines is called an isotherm. Each one of these curves. Okay? Isotherm means every point on each of these curves was taken at constant, represents data at the same temperature. So which one is carbon dioxide and which one is nitrogen? So let's just say which one is carbon dioxide. Is it A or B? Okay. That's 1/3, 2/3 split, huh? Okay, so correct answer is B. Why B? Well, what does a dip below 1 mean? When Z dips below 1, what does it mean? Attractive forces. You're looking at conditions where attractive forces are significant so that the gas occupies a smaller volume than it would if it were ideal, right? When Z equals 1 right here, that's the ideal case. So why do you expect carbon dioxide to dip below 1 better than nitrogen at the same temperature? Then you'll have to compare carbon dioxide and nitrogen in terms of intermolecular forces. Okay? So how do you compare carbon dioxide and nitrogen in terms of intermolecular forces? Remember the Lewis structures for carbon dioxide and nitrogen? This is carbon dioxide and nitrogen. They're both nonpolar. So the only type of intermolecular forces that's going to be involved there would be what? For nonpolar substances, what's the only type of intermolecular forces present? London dispersion forces. And what did we know about London dispersion forces? The larger the molecules, the more polarizable your electron cloud is. In other words, the bigger the air, the region where your electrons are moving around, the more likely you can have induced dipoles. You can have instantaneous dipoles. Okay? And so you have stronger attractive forces among carbon dioxide molecules as opposed to nitrogen molecules, simply because of its size. Okay? There's no dipole-dipole interaction here. Neither one of these is polar. There's no hydrogen bonding interactions. So the only source of intermolecular attractions here would be London dispersion forces. Okay? So, what typically happens to a gas, okay, if there's a certain temperature, okay, above which you cannot liquefy a gas, and that's called the critical temperature. So below a critical temperature, you can actually liquefy or change the gas to either a solid or a liquid by simply increasing the pressure. You can maintain its temperature, but you can turn it into a solid or a liquid by increasing its pressure. Okay, and that's illustrated here. This curve right here, pressure volume, okay, curve here illustrates gas that's liquefying as you change the pressure. Let's try to understand what these curves look like. This is what the plot that you would get if at a constant T. Okay, so these are what you call PV isotherms. These graphs right here. So it's a plot of pressure versus volume at constant temperature. So what does this ideal curve say? Pressure is inversely proportional to volume, right? That's Boyle's law. Imagine you have a gas with high volume right here, okay? Low pressure. What happens if you shrink your volume? Remember Boyle's law? Pressure goes down as volume goes up. Pressure goes up as volume goes down at the same temperature, right? So if I were to shrink my volume, what happens to my blue curve right here? It starts to rise, right? Volume goes down, pressure goes up. As I keep compressing my gas, okay, my volume keeps going down, my pressure keeps going up. Okay, that's the ideal behavior. Okay, now what does it mean when the real behavior is shown by this red curve right here? At this particular, let's say at this particular pressure right here, okay? At these 2 points right here, point A and point B. Point A is the ideal case, point B is the real case. What does that mean? The real volume is less than the ideal volume, right? V sub B is your real volume, and V sub A is the ideal volume. So what does this mean? That your gas is in such a case where attractive forces are important. So it's occupying a volume that's smaller than the ideal volume. But eventually what happens to that real gas? Okay, below a certain temperature, which we call the critical temperature, okay, eventually what happens to that gas? Okay, so again, the pressure still goes up, okay, as you lower the volume, okay, the pressure keeps going up. Eventually you reach a point though, okay, where, so let's imagine you have a gas right here, okay, you're trying to change the volume, you're lowering the volume of the gas, you're pushing it down, right? So what happens as you push it down? The pressure goes up, okay? So right here, your pressure will be going up as you're changing the volume. As you're lowering the volume, the pressure will go up. But eventually you get to a point where, okay, you can change the volume, but the pressure is not going to change at that temperature. How could that happen? That's the point where your gas starts turning into a liquid or a solid. So if you squeeze it some more, okay, the pressure is maintained because the gas molecules leave the gas and go into a solid or a liquid. So you're maintaining that pressure. So this flat line right here, okay, the pressure at this point is called the vapor pressure of your solid or your liquid, depending on whether it's turned into a solid or liquid. So this flat line right here is the vapor pressure of the gas of the substance at that temperature, at the given temperature. Remember, these curves represent what we call isotherms. So at this particular temperature we're looking at, that would be the pressure of the substance. Okay, it's called the vapor pressure. So eventually, what happens if you keep squeezing it? What happens? Everything turns into a liquid or a solid. Okay, and it becomes very, very hard to squeeze that solid or liquid. So you're going to have to apply a very large amount of additional pressure just to cause a small change in the volume of that solid or liquid. Okay, so on this diagram then you would say that a point on this curve right here would represent a solid or a liquid. A point on this curve would be a gas. Okay, this would be a solid or liquid. A point here would represent what? A condition where you have a liquid and a gas, or a solid and a gas in equilibrium. So at the same time, okay? So if this is the overall molar volume, this point right here would be the molar volume of the solid or liquid, and this point right here would represent the molar volume of the gas. So that's a typical behavior of a gas that, if you squeeze at a given temperature, will turn into a liquid or a solid. Okay. So let's look at this isotherm right here. Which of the labeled points, K, L, M, or N, would represent a condition where the substance is gaseous and deviates least from ideal behavior? This is pressure versus volume. Let's change this since your clickers have A, B, C, D, and E. Let's make this A, B, C, D, and E. Okay. So which labeled point on this diagram, this is an isotherm here, represents a condition where the substance would be gaseous and deviates least from ideal behavior? A, B, C, D, or E? Okay. Ideal gas behavior happens when? When did we say ideal gas behavior occurs? Low pressure. Okay, on this diagram, where is the low pressure? You want to try it again? Let's see. Okay, very good. Low pressure. Okay. So at point E, we said that, okay, this would be way over here. It's going to be ideal, right? So as you increase as you shrink the volume of the gas at constant temperature, the pressure is going to be going up, right? Which labeled point on this diagram represents a condition where you would have a solid or a liquid? The whole thing is either a solid or a liquid. A, B, C, D, or E. Very Good, point A. All right. Why point A? Remember we said that as you shrink the volume, okay, the pressure is going to go up. Eventually, it reaches a point where the pressure levels off even if you keep shrinking it, even if you keep squeezing it. And the reason for that is the gas molecules go into a solid or liquid as you keep squeezing it. But eventually what happens? Once you've squeezed it enough, okay, no more, you end up with no more gas. Everything's either turn into either a solid or a liquid, and it becomes, so from point K onwards, okay, everything's turned into a solid. So the correct answer there is actually what? A or B. Okay, so B would also be a correct answer. All right. What would be the vapor pressure of your substance? At what point is the pressure here equal to the vapor pressure of the substance? That would be the pressure at points K or L, right? So this is the vapor pressure at this temperature. Okay, here's a plot of Z versus P for a substance undergoing liquefaction, okay? Based on the dependence of the compression factor, we can say that this substance is below the critical temperature or above the critical temperature. This is Z versus P. This is an isotherm, so all of these data points are at the same temperature. Does this thing represent conditions below the critical temperature or above the critical temperature? Okay. Actually, I did say it was below the critical temperature, right? Below the critical temperature. Why? You can see that big dip right there. Okay, so that's another way of looking at this graph right here. Instead of pressure versus volume, you can plot Z versus pressure. Okay? And in fact, this pressure right here is the vapor pressure of the gas. Okay? So this is the vapor pressure. So that's the pressure of the gas that would be in equilibrium with either the solid and the liquid that you can. See, a drop, remember what is Z? It's a ratio of volume to the ideal volume, right? So when you see that drastic drop in Z in your isotherm, that corresponds to liquefaction or deposition. Deposition is the opposite of sublimation, going directly from a gas to a solid.
Even if, say, that graph had to drop above where 1 is,
Uh-huh.
would still be considered below the critical temperature?
If you see that drastic dip, okay, then you are below the critical temperature. If you're above the critical temperature, you might see something that looks like this. There is no big dip. Okay, for example, over here, okay, you can, if you're above the critical temperature here, you might see something that looks like that. It's still going to be less than ideal. If this was the ideal, okay, it's still going to be, your real curve is going to be, it might dip below ideal and eventually it's going to overtake the ideal curve. But if you don't see that horizontal line, you know that you're not condensing, you're not liquefying, or you're not turning your gas into a solid. Okay, so that horizontal line in a PV diagram, in a PV isotherm, is indicative of liquefaction or deposition. Vertical line on the Z versus pressure indicates liquefaction or deposition. Okay. So let's try to quantify our notion of real behavior now using what we call the van der Waals equation. Let's try to improve upon the ideal gas equation in terms of being able to describe the behavior of our gas. Okay, the van der Waals equation basically takes into account repulsions and attractions among the molecules, so you get a better explanation of the behavior, real behavior of a gas. So things to things to consider are the fact that molecules do occupy a finite volume due to intermolecular repulsions. You can only get those molecules so close before they start to strongly repel each other. Okay, so when they're as close as possible, then they start to strongly repel. So we say there's a finite volume around the nucleus, the nuclei of your molecule, where so you can think of that as a finite. You can consider your molecule as having a finite size. Okay, so because the molecules, so if I have this molecule right here, and I've got these other molecules here. Okay, this volume occupied by this molecule right here is not available for the other molecules to travel around in, right? So we say that the effective volume in your container that the molecules can roam around in is reduced by the volumes occupied by the molecules themselves. Okay? So the volume available for molecules to move about is reduced. And so if the volume available for molecules to move about is significantly reduced, okay, then the molecules will collide more frequently with the walls. And what does more frequent collision with the walls mean? Higher pressure, okay? So you would expect your pressure to be higher than ideal, okay? So if your ideal gas law says PV equals nRT, now V sub m here is V over N, okay? That's your molar volume. That's another way of writing the ideal gas law. Okay, so we can solve for the pressure. According to the ideal gas law, pressure is RT over V sub m. Okay, but because of excluded volume, okay, because of the volume that's non-available to the molecules, you introduce a correction term here. Instead of RT over V sub m, you write RT over V sub m minus B. So we introduce this correction factor, and that's called your excluded volume, and that is due to the size of the molecules. Okay, and you can, if you were to think of your molecules as hard spheres, then that would actually give you an estimate of the volume of the molecule. It's 4 times the molecular volume. Okay, the actual volume of the molecules themselves, not the volume of the gas, but the molecules themselves. Okay, now why does this correction not matter if you're dealing with cases where ideal behavior is observed? Well, at very low pressures, remember you say the molecules are very far apart, so the volumes occupied by those molecules are negligible compared to the total volume of the gas, the total volume of the container. But once you get them close enough, then these excluded volumes become a significant correction. It becomes a significant factor in terms of pressure. So there'll be more frequent collisions with the wall, okay? And so if you subtract a number down here from the molar volume, what happens? You're dividing by a smaller number, right? So when your denominator gets smaller, what do you expect? The whole expression here becomes larger. So that would lead to a higher pressure compared to the ideal pressure, okay? So your pressure would be higher than ideal. Now, what does it mean when the pressure is higher than ideal in terms of Z? So if the only thing that's happening here, let's say your molecules are not attracting each other, okay? Let's just ignore attractions for now. Let's just say the only correction we're going to look at is repulsions. Well, if that's the case, then you say the pressure would be larger than ideal. Well, if pressure is larger than ideal, you can say that Z is going to be greater than 1. Why? Well, remember repulsion we said will lead to a larger volume than ideal if under the same conditions. You can also say, another way of looking at Z is this. For the same volume, okay, for the same volume at the same temperature, the ratio of the actual pressure to what the ideal pressure would be is also equal to Z. So not only is Z equal to V over V ideal, that's also equal to P over P ideal. Okay? And here's how you can show that. It's a mosquito. Okay, so pressure over nRT over V, right? That's another way of writing PV over nRT. I'm dividing both numerator and denominator by volume. Okay? So I have pressure over nRT over V. This, for the same volume and temperature, this is what the pressure would be. Right? If you compare that to the actual pressure, P over P ideal, that's your Z. So Z greater than 1 also means that your gas pressure is higher than what it would be if it were behaving ideally at that temperature in that container. Alright, so Z is greater than 1. This is still consistent with what we talked about earlier when we said if volume is larger than ideal at the same pressure and temperature, Z is greater than 1. It has to do with repulsive forces. Z greater than 1 accounts for is due to repulsive forces. Okay? So we've got a slightly better equation here than the ideal gas equation because this one can account for repulsions. But we need to be able to account for attractive forces as well, right? So let's take a look at how we account for attractive forces. In addition to excluded volume correction, like I said, you need to account for attractive forces. So what do we have so far? What we have so far accounts only for repulsions. This is what's known as the hard sphere model, okay? So P is RT over Vm minus B. We said this is going to be larger than the ideal pressure, right? Now, pressure, if you recall, is due to collisions of your molecules with the wall, okay? So the more frequently they collide with the wall, okay, then the higher the pressure. The faster they're moving when they're colliding with the wall, the more energetic they are, the more force they exert on the wall, the higher the pressure, right? Now, what happens due to attractive forces? Let's imagine you have a molecule approaching a wall, okay? So this molecule is approaching the wall at, let's say, 400 meters per second. But you've got these other molecules over here that are attracted to that molecule, okay? So what will these other molecules do as this one molecule we're looking at approaches the wall? Will it slow it down, speed it up? Attractive forces. So it's going to pull back on that, right? So a molecule that would, under ideal conditions, a molecule would be approaching your wall at constant speed, right? But because of attractions from the other molecules in your sample, it's going to slow down a little bit as it approaches the wall. As it moves away from the other molecules, it's going to be pulled back by the other molecules, which are attracting it. So that would lead to lower pressure on the wall. Okay? So your effective pressure would be less because the attractive forces are going to pull back on those molecules that are approaching the wall. So in addition to this correction right here, we have to subtract, okay, from this expression something that would lower, you subtract something here so you can lower the effective pressure. So now the reduction in the pressure we say is directly proportional to the square of 1 over molar volume. What do we mean by 1 over molar volume? What's molar volume, did you say? Number of moles over, moles over volume over moles, right? So what's 1 over molar volume? It's number of moles over volume, right? So that's really concentration, moles per liter. So the reduction depends on the concentration, moles per liter, N over V. Not just on the molar concentration, but the square of the molar concentration. Because it depends on how many molecules within that volume, how many molecules are affected. They're all affected, right? So the more molecules you have, more molecules are affected. But it also depends on how many molecules are affecting the affected molecules. So that's why you have a squared term right there. So this is really, we say that the correction factor here, the correction term, is directly proportional to the square of the concentration of molecules. The more concentrated your molecules are, okay, the bigger the correction you have to introduce because of attractive forces. The more your molecules will tend to be slowed down as they approach the wall. And so that lowers the effective pressure. So this equation right here is called your van der Waals equation. Okay? So what's the effect of attractive forces on Z? It tends to make your Z less than 1, right? So you have a battle here between repulsion and repulsive forces and attractive forces. Whether Z ends up being greater than 1 or less than 1 depends on which type of force predominates, attractive force or repulsive force. So let's look at our units. If you look at your equation, P equals nRT, okay, it's RT over V molar volume minus B minus A times 1 over molar volume squared, right? What's our unit for B? B has the same unit as molar volume. Remember, it's excluded volume. So if you look up values for the van der Waals constant B, it's given in liters per mole. Okay? Let's compare the B value for O2 versus H2. This is 0.03186 liters per mole for O2. For hydrogen, it's 0.02665. Why is that? Which one's bigger? O2. Why is the B value bigger for O2? What's B and what does B tell us about the molecule? The size of the molecule. So O2, an O2 molecule is bigger than a hydrogen molecule. Okay? So on a test I should be able to ask you questions like that. If I were to ask you, okay, C6H6 versus CH4, which one has a larger B value? C6H6 is a bigger size, right? So B is a measure of the molecular size. In fact, B, we say, if you were to assume your molecules are spheres, it's 4 times the volume of the sphere, okay, of a mole of spheres. Okay, so you can estimate, if you can imagine your molecule as spheres, you can estimate the size of those spheres from the excluded volume. Now, what about the van der Waals parameter A? What's the unit for that? Okay. A times 1 over Vm squared must have a unit of pressure, right? Because pressure is equal to this minus that. So A over molar volume squared must have units of pressure. So how can that have units of pressure? What's the unit for molar volume? Liters per mole, right? So you square that. So what should be the unit for A so that the whole thing becomes a unit of pressure? It's a pressure unit, so something like atmosphere over liters per mole squared. Oops, times liters per mole squared. Okay. Oops. It's atmosphere times liters per mole squared, so that we can cancel liters per mole squared and you get atmosphere. So the unit is a pressure unit times liters per mole squared. Okay, bar is a unit of pressure. So how is a bar related to an atmosphere? 1 atmosphere is 1.01325 times 10 to the 5th Pascal, which is a Newton per square meter, remember. And 10 to the 5th Pascal is what we call a bar, so 1 atmosphere is 1.01325 bar. Okay, so let's look at these numbers right here. C2H6 versus CH4. Why is the value, the A, the van der Waals parameter A, larger for C2H6 compared to CH4? Why is this value bigger for C2H6? How does C2H6 compare to CH4? Bigger size, right? Bigger size, so bigger B value. But why is the A value also bigger? Attractive forces. What kind of attractive forces do C2H6 molecules have for each other? What do you call these molecules? What type of molecules are these? Polar, nonpolar? These are nonpolar molecules, right? The only type of attractive forces they have for each other are London dispersion forces. Okay? So what did we say about London dispersion forces? The larger the molecule, the bigger the region where your electrons are roaming around, the more polarizable, right? Which means that there's a greater you're gonna get stronger attractive forces. Polarizability means ability to form temporary instantaneous dipoles, right? So this one would have stronger attractive forces among the molecules as opposed to these smaller molecules. So in general, you'd say the larger the A value, the larger the B values, the larger the molecules, the larger the B values, the larger the A values. Okay? But what about water versus H2S? I think I have that right here. No, that's not water versus H2S. That's just H2S. Let's compare water versus H2S. H2O and H2S. Where do you find oxygen and sulfur in your periodic table? Group 6A, right? Column 16, oxygen is in second period, sulfur is in the third period. So, A or B, which one has a larger A value? And let's start with larger B value. Which one has a larger excluded volume, H2O or H2S? Okay. Which one's bigger? Going down a column, size of the atoms increases. So H2S would be a larger molecule. Sulfur is a larger atom than oxygen. Okay? So H2S would have a larger B value. Which one would have a larger A value? H2O or H2S? Which type of molecules would have much stronger attractive forces among them? That's another way of saying it, right? Remember, A value accounts for attractions. So for which molecules would you see stronger attractive forces? Intermolecular attractive forces. Among water molecules or among H2S molecules? Oh, 50-50, just about. Okay. Need to phone a friend. You remember what we said last time when we talked about intermolecular forces? Something about water being anomalous, right? What's the anomaly that's associated with water in terms of attractive forces? Water is made up of very small molecules, even smaller than O2 molecules, yet at room temperature it's a liquid, while as oxygen is a gas, right? H2S is a gas at room temperature. H2O is a liquid. Why? Because of hydrogen bonding interaction, you have an anomalously strong attractive forces among water molecules. Given that, let's see if you can, why don't you convince your neighbor your answer is correct and we'll redo the poll. Go ahead, you can talk. You ready to redo the poll? Okay. Which one would have a larger A value? Instant response, very good. That's water, has larger A values because of hydrogen bonding interactions. Okay? All right. The van der Waals parameters for H2S are 4.484 atmosphere liters squared per mole squared and 4.34 liters per mole. Which one is A? Which one is B? Okay, let's just answer which one is A. Is it A or B? Given those numbers, the van der Waals parameters, which one of those is A and which one is B? Go by the unit. Look at the unit. What should the unit be for A and what should the unit be for B? Correct answer. A should be atmosphere liters squared per mole squared. And B, remember B, we say is excluded volume, so it has units of liters per mole. Okay. Oh, there's a difference between H2O and H2S. Look at which one has the higher A value. Water has the higher A value, and which one has the higher B value? H2S. Okay, and what's the explanation again? Although we say in general, the bigger the molecule, the bigger the B value, the bigger the A value. Okay. The anomaly in the case of water is because it's capable of hydrogen bonding interactions. What other molecule do we know of is capable of hydrogen bonding? Remember, ammonia is also capable of hydrogen bonding. So these are the kinds of molecules you need to be alert to. HF. Okay. Anytime you have hydrogen attached to fluorine, oxygen, or nitrogen, okay, it should immediately, what's the word? Trigger something in your mind that says, that could be an exception. Okay, so I have to consider hydrogen bonding if we are looking at intermolecular forces. So, what would be the effect of temperature on the behavior of an ideal gas? Look at what happens here for nitrogen. Okay, at low temperature it dips and then it goes back up. Okay, at slightly higher temperature, this is 200 Kelvin. 500 Kelvin, this is a little warmer than room temperature. It dips, doesn't dip as much, and then it goes back up. Okay, this is Z versus pressure. What happens at 1000 Kelvin? It doesn't dip at all. It just keeps going up. Okay? So what do you notice? You get that dip at lower temperatures, okay? And then at higher temperatures, it doesn't dip, but it still goes up. So primarily then at higher temperature, what's mainly responsible for deviation from ideal behavior at high temperature? What's mainly responsible for Z greater than 1? Repulsive forces. Okay, you can never get rid of repulsive forces. There's only so much that you can. They can only get so close, and they start to repel. Okay, so there's always going to be that correction. But at low temperatures, okay, you don't have enough. The molecules are not going to have enough energy are not going to have as much energy to overcome the forces of attraction among them. So at higher temperature, we say the deviations due to attractions become less and less important. Okay? So higher temperature, attractive forces become less important. So the deviation from ideal behavior will reflect that. It's not going to dip below Z equals 1 as much as it would at low temperatures. But at even at very high temperatures, your repulsive forces are still going to be a factor. Okay? Now, if you're wondering where do they get these van der Waals parameters, the A and B, they calculate it from the critical point. Okay, experimentally determined critical point of your substance. So T sub C here is the critical temperature. So that's the temperature at the critical point, and P sub C is the critical temperature. It's the pressure at the critical point. So how is the critical point determined? Let's look at a PV diagram again to illustrate how the critical point of a gas is determined. Okay, again, imagine you have a gas. Okay, right here at very high volume. you compress your gas. Okay, so you have a gas. Okay, you push on that gas to shrink it. What happens as you shrink it? Pressure goes up, right? Eventually, it reaches a pressure where if you keep shrinking it, the pressure doesn't change. What does it mean when the pressure is not changing? That means your molecule is going into a liquid or a solid. You start forming a liquid or a solid, and then what happens eventually, as you keep pushing it, as you keep shrinking it, eventually everything turns into a liquid or a solid, and then the pressure goes up really fast. Okay, for you to be able to shrink it even more, okay, you're gonna have to exert a drastically very high pressure, because once your molecules are in a solid or a liquid, they're as close as they can be. Okay, it's getting too crowded. They get all these charged particles repelling each other. So what happens at a higher temperature? If you did this at a higher temperature, what you'll find is it's going to take a higher pressure before you can get the gas to liquefy or deposit as a solid. So we say that the vapor pressure, this is the vapor pressure at lower temperature. This is the vapor pressure here at a higher temperature. So the vapor pressure increases. Okay? But that's not going to continue. Eventually, what happens is you get a curve that looks like this, where you don't that flat area of your curve, flat region of your curve is going to get shorter and shorter and shorter. Eventually, you get this point right here, which is called the inflection point. That's called your critical point. In math, they call that an inflection point. Okay? And at that point, okay, you'd say beyond that temperature, beyond this critical temperature, you can no longer liquefy or solidify a gas by just increasing its pressure. So you have beyond this, you have what's called a supercritical fluid. Okay, so this point right here is your critical point. The pressure at that point is the critical pressure. The temperature at that point is a critical temperature. The volume at that point is a critical volume. And so based on the values of the critical temperature and the critical pressure, you can calculate the van der Waals constant. Now, how did they determine that? Uh, you have to use a little calculus there. At that point, you say that the derivative of the pressure with respect to molar volume is equal to 0, and the second derivative is also equal to 0. But we're not going to go into that. Okay, that's for an upper level class. Suffice it to say, that's where the values come from. Okay. All right. So let's talk now about phase diagrams. This might be a good time to pause, and we'll continue this the next lecture. Okay.